So, good afternoon, everyone. For the next session, we have with us Dr. Mohd Nadeem. He will be delivering his session on microfine material. Sir has done his PhD in civil engineering and currently working as an head alcofine in Ambuja Cement Limited. Sir has also worked in Hove India, a Canada-based consultancy firm. uh, Sir has technical affiliation with Indian Concrete Institute, Association of Consulting Civil Engineers, fellow member IE, Chartered Engineers, member Indian Society of Structural Engineers. Sir has published and presented 23 research papers in national and international conferences and journals. Sir research interests includes prefab construction, advanced RCC design, high-rise building, advanced construction material and concrete technology, HPC, SCC, green concrete, ultra-high strength concrete, light transmitting concrete, etc. Sir has delivered lectures and conducted workshops covering 5,000 plus professionals. Sir has visited many countries for exploring the construction technology, which include USA, Canada, Germany, Switzerland, France, Australia, New Zealand, Hong Kong, China, Singapore, UAE, Macau, Malaysia, Indonesia, Thailand, and Sri Lanka. Uh, Now I request Dr. Mohammed Nadeem sir to start with this session.
Yeah, good afternoon. So hello,
Yes, sir.
can I start?
Hello. Yes, sir. Yes, sir. You
Yeah,
can start.
yeah. So good afternoon, all the organizer team and all the participants. So my topic for today's presentation is utilization of fine and microfine binders, that is SCM, supplementary cementitious material, as a means to achieve durable, sustainable concrete. And of course, we are looking for 100 plus service life of a structure. So under this topic, I'm going to cover my presentation with these milestones. So I'll be covering the background, inside of the concrete, then microstructure, microfine supplementary cementitious material, what are the various durability tests, case studies, microfine SCM specification, and conclusion. So this is how we'll just cover that entire presentation under these heads. To begin with, of course, importance of concrete microstructure in the sense the properties of any of the material, irrespective of whether it is a concrete or any of the other material, which is governed by its internal structure. For example, if you see a steel, a slight, you can say, increase in content of a carbon, say normally, say for example, mild steel, you have a carbon content of less than say 0.25, so it is towards the mild steel. As carbon content increases beyond 0.3%, a slight, you can say, change in properties or a content in a microstructure level, and the entire property changes. So this is very, very important. If we want any properties to be changed, that needs to be work at a microstructure level. And this is the topic which we'll be covering in depth into today's presentation. So coming back to concrete, in concrete, porosity rules the properties. And that we'll see in subsequent presentation how important to address a porosity in concrete, which we want a long, sustainable, and durable concrete. And this microstructural understanding opens the world for better material processing. In the past, if you see in the future, in the past, Romans, they built a very long-lasting and durable structures. Uh, 2000 years back, they were using all those advanced material, which we call right now as advanced material. They were using it, fine and microfine materials, maybe in the form of pozzolanic material. And this is a reason, if we see all their structures are still intact after 2000 years. Based on the durability parameter, those structures are still intact and standing. So these are the, you can say, various properties of those material being used in that concrete to make a durable concrete. In modern times, also a lot of structure are being built. So many examples are there. I will not go into a depth of those structure, But like just to name Burj Khalifa, tallest building, even in our country also, a lot of infrastructure projects are coming up. Even tall structures are coming up based on utilization of those materials. Coming back to the definition of HPC, here we are talking about the high performance concrete where all those materials are being used. As per ACI, any concrete which is meeting the special combination of performance and uniformity requirement, which is not possible with a normal conventional concrete, is normally been referred as HPC concrete. And if you just see the history of use of HPC concrete after 1970, a lot of structure is being built by utilizing HPC concrete. Way back in 1973, Water Tower Place in Chicago, their concrete used was 62 MPa, and subsequently a lot of structure which came started using HPC with a high grade of concrete. So there is a difference. High strength concrete is not a HPC, but HPC is normally associated with high strength or high grade of concrete. So there is a clear cut differentiation which is being mentioned as per the definition of ACI. So these are the, you can say, list of various structures where high performance concrete is used. Again, here being used at a lower level and with a 90 days modulus of elasticity of 43 or 44 GPa for the core and outringers. Foundation was 3.7 meter thick, and these are the various you can say parameters. Across the globe, of course, if you just see Brillia Tower, Tokyo, where M130 grade of concrete being used. If you see another tower, Kosugi Tower, where M150 MP grade concrete is being used in those structures. In India also, nowadays, if you see a lot of tall structures are coming up, and for construction of those structures, HPC concrete is being used. For example, in Mumbai, Palaces Royal being constructed by using a M80 grade of concrete. World One, which is being completed, which is tallest residential tower in India. Again, here also, HPC concrete is being used with various specifications. Nowadays, this concrete is having a very special requirement on the basis of durability parameters, like RCPT values. Of course, is a self-compacting concrete with elastic modulus. Drying shrinkage requirement and strength. Of course, is a HPCVA, which high grade of concrete M95 with the mixed proportion is being mentioned below. So these are the typical mixed design for high strength concrete or ultra high strength concrete. These are the mixed design being used in Japan. There are various, you can say, proportions with various strength, right from M80, M100, M130, M150. Flow requirement is 650 or 600 plus with a cement of low heat cement. Water binder ratio is being restricted to the range of 0.25 to 0.15. Again, this is a cement and microfine material is being used along with fibers. Now, there are various advantages of using HPC or high strength concrete. So, this is a typical, you can say, a saving which can achieve by using high strength or high grade of concrete. So, if your existing grade of concrete is between 30 to 40, and if you replace with M60 grade of concrete, reduction of concrete is being estimated to the tune of more than 40%. Now, once you are reducing the concrete content, naturally your dead load is being reduced, and design or a structural engineer can understand if you are reducing your dead load by 40%, how much saving he will achieve in that way. With this reduction of steel component is also by about 39%. And of course, if both the things are being reduced, naturally your cost of construction is reduced not less than, you can say, 20 to 35%, depending upon the type of structure, span, and other parameters. Again, if you are replacing 40 MPa with 80 MPa with HPC concrete, reduction of the volume of structural member and static load is reduced by 30%. And if you are reducing your grade of concrete 60 to 80 MPa with 150 MPa, a lot of reduction happens. Whatever the above two advantages is being combined with the reduction in the column cross section. Naturally, your beam span will also increase, and there will be overall reduction in cross sectional areas. So, a lot of advantages are being associated if you are replacing your existing grade of concrete with the SPC and high grade or high strength concrete. And these are the performance expectation for uh, this kind of concrete. So what we are expecting, or what is the expectation from the, you can say, a client side or from the side for this type of concrete is, we are looking for a high early and ultimate strength along with high strength. That's why we are saying is not only a high strength concrete. Along with high strength concrete, lot of associated thing has to be achieved. So that is why it is being called as a HPC. So the next requirement is high Young's modulus, low creep, because a tall structure naturally creep coefficient should be as low as possible. High workability and rheology, low permeability, sulfate and chloride resistance. There should be a frost resistance. There should be a chemical resistant and abrasion resistance. So these are the performance expectation of a modern day of a, structure which is being built. And if those are the performance expectation, naturally specification is being now a typical specification for a concrete nowadays are like this. Elastic modulus of a 56 days in the range of say 54 GPa gigapascal, drying shrinkage of 28 days less than 0.025 or in the range of 0.025 to 0.0325, creep coefficient as low as possible in the range of 1.6 to 1.7, RCPT rapid chloride penetration less than 1000 coulomb, ISET surface absorption test. Again, the requirement from the durability perspective 0.065. These are the typical specification being mentioned nowadays to all the key structure where HPC concrete is being used, where we are looking for a design or a service life of more than 100 years. Water permeability less than 10 mm, chloride diffusion less than 1000 into 10 raised to 15 meter square per second. Flow, of course, nowadays majority of the concrete are of a say flowable concrete or a self-compacting concrete, where initially we are looking for a flow of a speed of 700 mm. So no longer people are specifying in the name of slump. Nowadays, now it is in the way of flowability, of course with the retention of 2 hours and 3 hours, because normally it is being done with the transit mixer. So whatever time required, so a good retention is always required in that concrete. Temperature, of course, at a time of pouring we are looking for less than 30 or 32 degrees centigrade, and grade of concrete is in the range of this thing. OPC content or a pure cement content is being restricted to 450 kg. For all the specification are going towards achieving a design life or a service life of more than 100 plus years. So these are the specification nowadays being specified in majority of the structures or a concrete to achieve those kind of serviceability or a service life or a design life of concrete. Coming back to our cement now, slowly we'll just explore the microstructure of a concrete. In that way, coming to the cement, if we just see the chronology or a time period of a cement, normally cement there are four compounds, and among them tricalcium silicate and dicalcium silicate are the, you can say, a cementitious compound, which it later stage react with the water and gives the CSH a gel or compound which impart the strength. If you just see the year, earlier if you just see, red one is the tricalcium silicate and blue one is the dicalcium silicate. Earlier trend where the tricalcium silicate was on the lower side, maybe around say 20%. Dicalcium side, dicalcium silicate was on a higher side, say about 50%. Now, silicate gives the early strength, but a lot of heat of hydration happens because of this reaction. On the other hand, dicalcium silicate is giving a strength, a little slower strength, but in that way, heat of hydration is on a lower side. But as the time progresses and as the need started coming for the high strength or high grade of concrete, all the cement companies started focusing on increasing the percentage of tricalcium silicate. So if you just see year wise, every you can say a decade, a percentage of tricalcium silicate in cement increases. So nowadays it's more than 60% of a tricalcium silicate, which started from 20%, and dicalcium silicate, which started say 1920 from 50%, now it has reached to almost say 15 to 17%. But one side we are getting a very good strength from the cement side. Nowadays, good OPC is giving a strength of say 60, 65, or 70 plus MPa also. But on the other hand, lot of drawback is coming by this strength. One is the heat of hydration, autogenous shrinkage, and lot of other durability issues are coming. But of course, we can't, you can say, think of going back, because nowadays the requirements are there for the high grade or high strength concrete. But there are other drawback or disadvantage which need to be addressed with other, you can say, means, which we are going to discuss. And of course, the cement efficiency is also increased. For per kg cubic meter, it gives 0.22 MPa, even more than that. This is the typical particle size distribution. The graph shows the size of the particle in terms of percentage available in a cement. So typically, if you see the OPC cement, the 90% of particles are less than 73 micron. 73 micron. 50% of the particles are less than 25 micron. So these are the range of a particle present in a normal cement. So in the range of say 25 micron to 73 micron for the sizes of D 50% to 90%, and 95% it is say 93 micron. So 95% of the cement particles are below 93 micron, just to understand in other way around in a cement. Of course, the range of a particles are zero point 0.4 micron up to 110 micron. But majority of particles, say average of a particle size, are in the range of say 25 to 30 micron in a typical cement. Just to understand the reaction, of course, we started now understanding the microstructure. These are the various sizes of particles. So we just saw a various range of particles present in a cement, say in the range of say around 0 0.4 micron up to 110. But there are various size of say 25 micron to 30 micron. But there are various range of particles are available, and each particle, depending upon the size, reactivity is different. So if you just see a 2 micron of a cement particle, and on the top row, it shows the time. So after 0 0.3 hour, 1.3 hours, how this cement particle start reacting once water is being added in a cement. So slowly and slowly it gets reacted. This is 4.8 micron. This is below of this micron. If you again further look into that particle, so one is a typical particle of say 2 or 3 micron, and once it gets reacted with water, slowly and slowly you will find this is anhydrous unreacted tricalcium silicate. This part is reacted, and slowly if you cut deep inside the particle, you will find this is how it start getting reacted. But lot of shrinkage, lot of pore uh, uh, is happening in this reaction. We'll see subsequent slides. So once reaction is happening, but parallelly each particle is reacting, but lot of shrinkage is happening, lot of pore uh, creation is happening in the particles, because whatever water we are added, 50 to 60% water only gets into a reaction, otherwise it gets just evaporated, and which creates lot of pores in cement or concrete. So this is how a cement particle, and this much size of a particle gets reduced into a hydration product after say 24 hours. And here you will just able to observe once these particles are getting reacted uh, to form the different compound in the form of CSH, calcium hydroxide, and other compound, and lot of pores are being created in these particles. A lot of pores are being created. So just to understand, this is a phase of a cement. So there are four major compounds. Majority are in the form of tricalcium silicate, which just now we understood. Dicalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite. With various reaction, ionization happens, and it is being converted into these compounds. So majority of the compound is calcium silicate hydrate gel, 48%, which is a compound which actually impart the strength to the structure. Then these are the anhydride or unreacted product. These are the pores we just observe because of evaporation of the water, internal this thing, lot of pores are being created. These are the other compounds. Here is the calcium hydroxide. This is the atractinite. This is a calcium aluminoferrite phase. So these are the various phases being created out of these four major compounds. This again other way of looking to that reaction. So if you see on the x-axis is a time, and these are the four major compounds. Once you add the water, and slowly if you see that changes happening with respect to time. So now this is a majority of the compound is dicalcium silicate. Slowly and slowly it gets converted after some time. This is a 100 days time. So majority of the material is being converted into CSH gel, Portlandite means calcium hydroxide, atractinite, and other compounds. So CSH and CSH is in the range of 65%, and 25% are atractinite and aluminum ferrosilicates. If you see the microstructure of a cement, so now you will observe all those compounds like this. So we saw we have a tricalcium silicate, we have calcium hydroxide, which is unstable. We have an outer shell of calcium aluminum silicate hydrate, CaSH. This is a porosity, this is atractinite, and this is how the various phases you will find in cement also after 28 days. And slowly it will get reduced. So a combination of pores, then we have calcium hydroxide, which is a unstable compound, and these are the you can say CSH gel and other compounds. So if you begin with this, so in the beginning we have a 40% of a cementitious material or a material in the form of sand aggregate and this thing. 60% is in the pore this thing, and it is being converted later on with 80% of a solid volume, 20% in the white volume. And these are the you can say normal reaction happens with OPC H2O. You will get a CSH, and then we have a calcium hydroxide, which is a weak compound. Now CSH form a strong paste to bond all the aggregates together. So this is a compound which imparts the strength in concrete. But because of this reaction, a lot of heat of hydration gets evolved. Now 50 to 60% of a water, whatever a water we add, say water cement ratio of say 0.3, 0.35, zero point 0.4, or in a high grade of concrete nowadays we are using a water cement ratio of say 0.2 also. So 50 to 60% water only takes part in hydration reaction. Rest of the water gets evaporated, which creates lot of capillary pores, which we need to address. Which we want a very, if you want a concrete to last long for us, say 100 plus of a life service life, then we need to address those issues, which we'll discuss in subsequent slides. So these are the particle of a cement being converted into a compound. But now you will observe a lot of porosity is being created. If you just see at a micro level, a lot of tunnels of pores are being created here. This is a size of 2.5 micron only, but inside you will find a lot of porosity. So if you convert this tricalcium silicate compound which is reacting with water and forms the CSH gel. If you combine calcium hydroxide also, even from that perspective, there is a reduction in the volume. And this reduction is in the form of evaporation of the water. See, for tricalcium silicate, the delta is coming by 3.6%. Now, this 3.6% is nothing but remaining porosity. Coming to dicalcium silicate, which is reacting with water, forming a CSH and a byproduct in the form of calcium hydroxide. Again, there is a delta of this much 0.4% of a delta. Now, this both the delta are nothing but porosity is being created in a concrete. So if you again see our structure at a micro level concrete, you will find this B is belite, dicalcium silicate, A is elite, P, this black part is pores. So whatever the this content reduction is happening, which is happening in the form of evaporation of the water, which is being created in the form of pores being remain in the structure. So this is how the porosity. Now coming to the porosity is nothing but the amount of air filled space in the material. So in any of the structure, whatever the remaining portion being there in the concrete, which is air filled, is called a porosity. Now what is the difference between porosity and permeability? Now permeability is the ability of the fluid to move in the porous material. So just to understand that concept, now if you see left side of a picture and right side of a picture, both the way, you have a both porosity, same porosity or whites. But the difference between this is left side is not interconnected, right side is connected. So if you say in terms of porosity, both are same at a level because air filled in both the pores are same. But in terms of permeability, what we understood what is permeability is the ability of fluid to move in a porous material. So it is actually giving a passage to move inside. So what are the things are moving? A lot of chemicals, water, and that we'll understand later, which gives passage to enter into a concrete. So even though if you have a porosity in your concrete, if it is not connected, is fine, is not much harmful. But if it is connected and giving way or passage, then it is quite harmful, which allows lot of material to ingress. So if you see porosity wise, both are same. But in terms of permeability, left side is less permeable and right side one is high permeable. So it's having a low permeability, right side of a material or a structure is having a high permeability. Just to understand a difference between porosity and permeability. So there are five types of pores being created in any of the concrete having a different sizes. So first one is the entrapped air, another one is entrained air, and which is in the range of 10 micron to 250 micron. These are the sizes of those pores. For capillary pore, the sizes are in the range of 3 micron to 30 micron. Now just go back and just remember our particle size distribution of a cement. Cement, we saw average particle size is in the range of say 20 to 30 micron, this one. So beyond this, though particle sizes are there, but majority are at a level of say 25 to 30 micron. What about these, you can say pores, which we need to address? Even for normal supplementary cementitious material, particle sizes are in that range only. Now there are gel pores with a size of 1 micron to 3 micron. And there is a fifth one, intercrystallite pore, which is about say 1 micron or 1.2 micron. So these are the various pores in a concrete which we need to address. Coarser one we are addressing with cementitious material. This one we need to address with some other material. So you can't address all the pores with one material or one way of you can say giving a solution. We need to have a different staggered solution to address those you can say type of issues arising in our concrete. So we have a porosity. Naturally, we can't avoid porosity because OPC is being used. It is reacting with the water, giving us a CSH along with unstable compound in the form of calcium hydroxide. 50 to 60% water is being used in reaction. Rest of the water gets evaporated, which creates. Naturally, in high grade of concrete or high state of concrete, porosity is on a lower side, maybe in the range of 5 to 6%. But in a low quality or low grade of concrete where water cement ratio is not being controlled, porosity is as high as 15%. So both the things we need to address in a concrete if you want a long lasting concrete. Now, what are the, you can say, drawback, disadvantages of these pores? Naturally, once you have a connected pores, which we understood is being called as a permeability, which are interconnected. Naturally, these are the, you can say, elements which will try to enter. These are the environmental, you can say, pollutants, acids. These are the sulfates, maybe in the form of internal, external also. These are the chlorides, carbon dioxide, and water. So these elements are trying to enter into the concrete through the pores. Once you have a higher permeability, naturally ingress will be quite fast. And subsequent reason, subsequent, you can say, reaction happen in the form of, say, carbonation or a corrosion of reinforcement. Once carbonation layer is being disturbed, naturally it comes towards the acidic one. And once chloride and water ingress happens, corrosion start to the reinforcing steel. And these are the, you can say, deterioration of the concrete structure. So corrosion, once corrosion start, it swells to the tune of, you can say, 5 times, 5 to 6 times of its original volume. And it creates a lot of pressure on the surrounding concrete. Initially cracks happen and then spelling of the concrete starts. So these are the, you can say, deterioration happens with the concrete if those permeability, those porosity are not being addressed. Maybe it happens after, say, 5 years or 10 years down the line. Now, what are the, you can say, steps to improve the durability? There are four major steps which we can address to address those durability issues and improve the durability. One is to reduce the porosity, which we understood. Porosity is basically from the paste component of a concrete. So by using microfine material along with the cementitious or supplementary cementitious material. So by using a pure supplementary cementitious material in the form of normal fly ash and GGBS will not work along with cement. You need to add microfine material because there is a gap gradations. We just saw the sizes of particles and the porosity sizes. To address that, you need to add the microfine materials. Of course, reduce the water cement ratio, reduce the calcium hydroxide generation in the form of utilization of those compound by using SCM. So with the pozzolanic action, it is the pozzolanic material reacts with calcium hydroxide and convert into again a CSA gel. And of course, increase the packing density of a paste component because you have a certain sizes of cementitious material which also has a lot of porosity that we need to fill with the final material. So these are the four basic steps to improve the durability. Now, HPC is made with these materials. Of course, you have OPC, then you have water, coarse aggregate, fine aggregate. You have chemical admixtures, water reducing admixtures. You have supplementary cementitious material in the form of GGBS fly ash. Then you have a microfine supplementary cementitious material in the form of ultrafine. We have one product, alcofine, microsilica or metakaolin, and fibers being used in a concrete depending upon the requirements. Now, binders being used in a concrete, of course, you have a Portland cement, which we can't avoid. But along with Portland cement, naturally, we have to use the pozzolanic material in the form of either a fly ash or a GGBS. So we end up with blended cement. Naturally, once you have blended cement, again, this blended cement is not enough to address the need of the durability of a service life more than 100 years. because a lot of porosities are there which is not being addressed by these materials. Naturally, you have very fine pores which need some other material, which is in the form of microfine material, in the form of either microfine flash, microfine GGBS, or a metacooling or microsilica. So combination of these materials will address those issues. So this is a binders combination of all the materials. So once you have this material, so we have OPC and silicates. With the water, the formation of CSH happens, and byproduct is in the form of calcium hydroxide portlandite, which we don't want, which is unstable. It react again with maybe with carbon dioxide and leached out by forming calcium carbonate. So we don't want this product, which is unstable. Again, we want to react with pozzolanic material. Again, it reacts and form the CSH. These are the cycle of component for the durability. So this is a reaction been explained with OPC, water, CSH, and byproduct in the form of calcium hydroxide. Again, CSH being formed, which is a very strong paste which binds all the aggregates together. But again, once you have calcium hydroxide, that is to be utilized by way of supplementary cementitious material, either GGBS, flash, microsilica, ultrafine GGBS, or alcofine, and again it forms the CSH gel. So this is a primary hydration, OPC, water, and this is a secondary reaction. So whatever the calcium hydroxide, again it react with water and pozzolanic material, silicates, and again it gives the CSH or CaSH, calcium aluminum silicate hydrates products. Again, this is a you can say cementitious material which imparts the strength to the structure. So SCMs are like vitamins for the concrete. Like for human body, we have a basic components which we need to consume in the form of proteins, fat, and carbohydrate. But along with this, we need a lot of vitamins to maintain a lot of functions. Similarly, in concrete also, one side we are using a cement, but along with cement, you need normal SCMs along with microfine SCMs. So combination of this thing will act like a vitamin in concrete that is to be used. So you can't think of using only fat, protein, or carbohydrate. You will sustain, but for the long serviceability, a life without a disease, naturally you need to consume a lot of vitamins. And for structure also, along with cement, we need to take other SCMs also. SCMs also in the form of normal SCMs and microfine SCMs. So these are the supplementary cementitious material. So at a macro level, pozzolanic materials are flash and GGBs. At a microfine level, we have microsilica, metacooling, rice husk, or ultrafine slag. We have one product, alcofine. If you just see the SCM micrographs of those materials, so left side if you see condensed silica fume, this is metacooling, this is alcofine 1203, and this is microfine flash. So these are the microfine products being used in concrete. In terms of permissible upper limits of SCMs, so flash, we have upper limit of say 35%. GGBS upper limit is 70%. Ultrafine SCMs, of course, those material comes under the head of flash or a GGBS, but normally it is used in the range of say 5 to 12%. Maybe ultrafine GGBS or alcofine or silica fume. It is used in the range. Normally, the dosages are in the form of say 7 to 8%, which gives quite a good result along with supplementary cementitious material and OPC. These are the effectiveness of various SCMs. Naturally, each SCM is having different aspects. So coming to resistance to alkali silica reaction, on carbonation resistance, on chloride resistance, on sulfate resistance, on resistance to industrial waste. These are the supplementary cementitious material performance. So in that way, GGBS is performing among all the SCM the best in all the parameters. These are the particle size distribution of various materials. So we have a microsilica, flash, cement, metacooling, ultrafine slag means alcofine. And these are the particle size distribution, various particles in terms of sizes being distributed. and it clearly shows alkofine is quite fine compared to all other material present. Of course, microsilica is submicron, but microsilica is not available in pure form because sizes are in the range of say zero point 0.2 micron to 0.0002 micron. So quite a fine material, but it is suspended. So practically, it's not possible to use that material. So it is densified. So densified, once it is densified, the sizes gets increased. So in a normal size, if you see a cement particle, if you see this is a cement particle, see average size is say 25 to 30 micron, and these are the microfine materials. So combination of these things. So if you see at a micro level, even for cement particle, lot of voids, lot of gaps are there in between. So to fill those gaps, you naturally need a microfine material to go inside this, because in between, if you add water, water gets entrapped here and which is not being used. So it is fine. There is an experiment when you add microfine material inside this cement matrix, water gets no, taken away from this combination, and you will get a lot of flowability in that matrix. So this is the advantage of adding microfine material into a cementitious paste. These are the combined particle sizes, actual pictures of the particles. So these are the cement, larger particles are cement particles, and inside these are the microfine materials. Microfine materials. Looks like an aggregate, but this is a cement particle at a micro level. So this is how the particle density works. So these are the cement particle. Naturally, we just saw into a SCM pictures micrographs. A lot of voids are there inside. So just to fill those, you need a microfine material. It goes inside, and it is how optimum packing is being achieved. So microfine material works in both way. One is mechanically by going inside, fixing those smaller gaps. So mechanically, it is actually enhancing the packing density. And then chemically, it is reacting with uh, calcium hydroxide, and again making a secondary gel reaction. So both way it is reacting and giving the advantage of those, you can say, materials. These are the, you can say, optimum particle packing density of binders is basically dependent on particle size distribution of all the binders, including that of cement, particle shape and size, chemical and mineralogical composition, loss on ignition, uniformity, consistency, and dosage or proportions. So these are the particle size distribution of all the elements being available in a cementitious matrix. And if you just see, this is a particle size distribution of a cement, and this is a particle size distribution of a alkofine 1203. So quite fine. So a lot of pores are being filled with this material. So whatever the gap gradation happening at a cementitious level, which is being filled with microfine material. Like in aggregates, normally we work on the gap gradation, in the sense we are working on the packing density, sand 10 aggregate, 20 aggregate. But this packing density is at a micro level. If you see the uh, okay, it's not visible. Now there are various tests is being done with the reactivity of microfine materials. So these are the three product being used: alkofine, metakaolin, and silica fume. And there is a test as per ASTM, as per IS 1727. So these are lime, alkofine, and these are pozzolanic material, and these are standard sand. 1:3 proportion mortar cube is being made with the water based on the consistency, and then compressive strength is being changed. It actually gives the indication of reactivity of a pozzolanic material with lime. So one side is alkofine, giving a compressive strength of say around 13.8 or 14 MPa. Metakaolin is giving 2.47. Silica fume is giving 8.5, which indicates the lime reactivity or reactivity of a pozzolanic material with lime. So here reactivity is. So this is how the latent hydraulic reaction of slag. So slag, you have a advantage of, there are two advantages. One is like whatever the calcium hydroxide is coming out as a byproduct with the reaction of OPC with water is been again reacted with the availability of pozzolanic material. On the other hand, even GGBS is also having a latent hydraulic properties. So both way it is reacting. And this is how if you see the matrix of a normal OPC, which gives a image like this, which is very porous in that nature. But because of this secondary reaction, there are a lot of pozzolanic reaction and latent hydraulic reaction is also happening. Hydraulic cementitious reaction is happening, which gives a very solid marks in a concrete. Coming to pozzolanic activity as per ASTM C12402, again here a cement is being replaced with 50%, 15% with various microfine materials. So this is ultrafine GGBS or alcofine, silica fume, or metacholine, and its strength is being checked with reference to the reference mix. So reference mix gave 22 MPa. Against that, alcofine gave around 32 MPa, silica fume 29 MPa, methacholine also around 29 MPa. So these are the tests being conducted for knowing the pozzolanic activity as per ASTM. Now there are various tests to check the chloride permeability, because chloride is the you can say a material which directly attack on the reinforcing steel and starts corrosion, which is very, very important looking to the durability aspects. So whole of our attention is towards reducing the porosity so that chloride ingress will be at a lowest level. Now there are various tests being developed to test the permeability or the penetration of the chloride. So this is ASTM C1202 RCPT, which is a very popular test. Normally, majority of the sites are nowadays using this RCPT. There is a 90-day ponding test where a slab is being made of a same concrete and a solution of NaCl is being poured over the slab concrete, and it is observed for 90 days. And once after 90 days, the slab is being broken into a pieces and penetration of the chloride is being checked. There is another test, chloride bulk diffusion. There is another test, rate of absorption and migration test. There are various tests. We'll just see few of the tests. We'll just discuss. So this is our most popular test, RCPT. Popular is in the sense it's quite fast. So one side, this is your concrete, size of 100 diameter and 50 mm thick of a concrete. One side there is a solution of NaCl 3%. Another side is a solution of 0.3 sodium hydroxide, and then current is being is being passed from one end to another end with a fixed voltage of 60 volts. Naturally, current is nothing but a passage of charges. Whatever the charges are there, it passed. So not necessary a chloride ion is passing. So this is a major drawback of this test, RCPT. So whatever the charges being passed, being measured here in the form of coulombs. Coulomb less than say 1,000 is being considered good, 1,000 to 2,000 you can say average, and above 4,000 is called poor. So these are the ranges being mentioned. But drawback of this test, a lot of drawbacks are there. So these are the common drawback, because in RCPT, we are calling it as to resist the chloride ion penetration, but actually it is measuring the passability or a conductivity of a electric charges. So whatever charges, not necessarily a chloride charges. There are many OH charges, OH ions. So many ions are there which passes. So even ASTM 1203 in clause 1 says test method is applicable to types of concrete where correlation have been established between this test position and a long-term chloride bonding test. So what ASTM is saying, if you want this RCPT, which is quite fast, if you are conducting this, before that, you have to make a correlation between the bonding test, which is a 90 days bonding test. So whatever penetration is happening in bonding test, compare this and draw a correlation and then use it. And there are various, you can say, clause, like suppose if you are using an admixture of calcium nitrite, again it gives a very different reading. So, and another thing is, even uh, their precision statement allows for a variance of 42%. So your results are coming, even though your results of a same batch of concrete from the same laboratory is coming, a variance of 42% is acceptable. And if that sample is tested in another laboratory, variance of 51% is allowed. So these are the drawbacks of this test, unless and otherwise it is being tested with a correlation. So these are the various, you can say, drawback of this test. If you are purely using this test, which is not being recommended even as per ASTM also, which we need to draw a correlation of a same type of a same grade of concrete. Even this is a, you can say, conclusion from the, you can say, various experts also. So those who are specifying RCPT value independently is not being recommended. It is to be done along with 90 days of a ponding test, make a correlation, then test this for the rapid chloride migration penetration test for the concrete. So if you see, we tested it. So in one way, in one microfine, it is giving a value of say 700, and in other case, it is giving a 1500 as per RCPT. Once we did a pond test, now with the pond test, values are totally reversed. If you see pond test, the values are quite low as compared to the RCPT values. So these are the drawback. Unless and until we draw a correlation of RCPT with ponding test, actual you can say test with the same concrete, otherwise such misleading you can say results will come if you are using independently RCPT. Coming to sortivity test, again this is indication of absorption, which is along with the chloride migration. Again here we are checking the absorption of the water. Naturally, indirectly it is checking the permeability of the concrete. So once you have a pores, if pores are interconnected, naturally permeability on a higher side. So higher uh, absorption will happen. If your permeability is on a lower side, your absorption will be on a lower side. So this is again a soft sortivity test. Another test is water permeability. Again, here 0.5 MPa of a hydrostatic pressure is being maintained for 3 days, and afterwards the sample is being broken and water penetration depth is being checked. So normally less than say 20 mm is recommended, but for all the structure where service life is more than, say, it is designed for more than 100 years, water permeability of say 10 to 15 mm is normally being recommended. This is another test of water absorption. Of course, all these 3-4 tests are, you can say, indicating the same thing. Your porosity or permeability of your concrete, ingress of water is being measured. Lower is always recommended. These are the assessment of workability. Comparison is being done between silica fume and ultrafine slag, and these are the, you can say, results. So naturally, with compared to silica fume, it gives a better workability in terms of water demand. Also, it gives you can say better retention as well as reduce water demand. So this is how alkalinity of the pore solution is being maintained, because if you are using ultra-fine slag, naturally 1203 is ultra-fine slag, where calcium oxide is in the range of 34% and calcium oxide content in OPC is 63%. So both way it gives the, you can say, results. So both way it is reacting with calcium hydroxide and giving the denser, you can say, pore matrix. It restricts the chloride penetration and alkalinity of the structures. And these are the protection from the corrosion of reinforcing steel. Particle packing, we already, you can say, understood earlier also. So because of this microfine material, it actually reduces the capillary pores, in the sense connectivity of the pores are being reduced. So one side, if you have this picture, which is all the pores are interconnected. Once you add a microfine material, naturally microfine material, you can say block those pores, and you have a pores maybe in a minimal, you can say, percentage, but those pores are not interconnected. Once it is not interconnected, naturally this will not allow a passage of other, you can say, ingredients which we saw, either in the form of chloride, sulfates, water, carbon dioxide. So it's always, you can say, useful to use the microfine material, which reduces the pores and improve the, you can say, permeability, lower the permeability, and it's always, you can say, better for the structure. So what are the, you can say, durability improvement due to microfine additives? So there are a lot of, you can say, advantage by using microfine material in a cementitious material. So in a fresh state, it improves the workability, improves the rheology of a mix, reduces segregation of a mix. It also reduces the heat of hydration, because once you have a OPC, it gives a lot of heat, which gets reduced by addition of microfine supplementary cementitious material. At a hardened stage, we just saw a lot of improvement happens with respect to durability. Once you are reducing the pores, reducing the permeability, naturally you have a lot of advantages. It also improves resistance to aggregate silica reaction. It also improves its strength, which we saw. It also improves to chemical attack and corrosion, and also lowers the permeability. So I'll just share a few of the, you can say, case studies where this product is being used. So this is a MTHL, a Mumbai Trans Harbour Line project, where 22-kilometer bridge is being under construction from South Mumbai to New Bombay. It is connected, and this is the longest bridge in India. So that project is completely in a very aggressive environment. So they also have a very stringent durability requirements, with a service life of say more than 125 or 150 years of this kind of structure. So the parameters for the durability specification were for there they use RCMT, because just now we discussed RCPT is not a right test unless and until there will be a direct correlation of a bonding test. So nowadays, this test is being used, which is directly measuring the chloride penetration. So RCPT is actually not measuring the chloride penetration, but actually measuring the flowability of the charges. So that charges may not necessarily be a chloride. So this is a test nowadays being used, being recommended and used, RCMT, which actually measures the penetration of the chloride. So RCMT coefficient of less than 2 into 10 raised to minus 12 is considered very good. 2 to 8 is considered good. 8 to 16 is normal, and above 16 is poor. So that structure, for the substructure, their requirement was less than 2 into 10 raised to minus 12 meter square per second is the coefficient. So that was in the specification for the substructure. And for the superstructure, specification was from 2 to 8, means good one, this one. And water permeability in the specification was less than 10 mm, and ISET was there in the specification with 0.25 ml per square meter per second. So these were the durability specification for that project, and which is being achieved. And they also use they are regularly using the alcofine, though the grade of concrete was in the range of M45 up to M55. But their requirement was from the durability perspective, with a service life of more than say 125 years. Naturally, they have to use all the microfine material also, just to get those specifications from those perspective. This is a underground metro. Again, here the requirement was early high strength. So they were looking for, because in an underground metro, after this TBM boring happens, naturally it is to be covered with the liners, concrete liners. These are the precast liners being, you can say, fixed with the six pieces, complete this diameter. This, and of course, underground metro also is also being designed for a service life of more than 100 years. So for this liner, they were looking for early high strength, 12 MP and 12 hours, because just to reduce the cycle of, because the precast one. So naturally, mold are to be used on a regular basis and in a reduced cycle. So the cycle was 12 MPa, 12 hours. And of course, they had a durability requirement for RCPT less than 1000 coulomb water permeability, less than water penetration less than 12 mm. And this is how it is being, you can say, recommended alkofine is being used for this project. This is again a very good, you can say, project, Mandavi Bridge in Goa. There also their requirement for HPC was 20 MPa in 24 hours. RCPT less than 1000 coulomb, water permeability less than 15 mm. Here also alkofine is being used in that project. This is a concrete mix design. If you just see the cement, the M60 grade cement is only 225 kg, 200 kg of GGBS, and 25 kg of alkofine. So nowadays, things are coming for a durable concrete. You have to reduce the OPC content as less as possible. So only 225 kg, 200 kg of GGBS, because all supplementary cementitious material is found to be very good in achieving those durability parameters. So more than, you can say, of course, if you just see compare 50-50%, 50% cement, 50% SCM. Alkofine is 25 kg, is a microfine material, and GGBS, normal GGBS of 200 kg. And this is the mixed design. These are the, you can say, requirements of a slum in the initial phase. Up to 90 was collapse, 120-minute 180 and 150 mm 2 hours. Strength, of course, these are the actual strength. So M60 grade, 28 days average is being achieved more than 64 MPa. So this 69, 47, 25, and these are the RCPT values. Less than 1000 was specified, and on an average they got 725. With a water permeability less than 15 on an average they got 9 So these are the, you can say, specification they could able to achieve. This is another project, tall structure in Mumbai. Again, high performance concrete, M60. Their challenges were mostly for the pumping at to that height, and of course other requirements of elastic modulus and creep. Naturally, you need to use along with cement all the supplementary cementitious material and microfine material also to achieve those specifications. So now just to, you can say, come to the end, whatever just now we discussed and we saw, which is not possible without utilization or using of fine and ultra fine material along with concrete chemicals in cement. Otherwise, whatever structure we discuss and which we saw, and maybe the structure which will come in future, is not possible unless and until all those ultra fine and microfine material are not being used, which is not possible, along with the, you can say, water reducing admixtures also one component to achieve those, you can say, specification in a concrete. So just to conclude, for proper particle packing, microfine or ultrafine material have to be used in conjunction with fine material, which we saw. Just if you want to reduce the porosity and permeability, we need to use those microfine materials along with cement and supplementary cementitious material. Shape and size as well as distribution, particle size distribution of fine and ultrafine material is playing a very, very important role in workability, cohesiveness, and pumpability. In HPC, fine and ultrafine play a very important role, which we discuss. Role to strengthen the interface between the binder paste and the aggregate, which is very important in high grade or high strength concrete inter transition zone. Free water and entrapped air get reduced in binder paste when fine and ultra fine material are used, and also this also reduces the shrinkage, because in higher strength or high grade concrete our cementitious content is on a higher side. So another issue comes in the form of shrinkage, but once you have a microfine material in that, shrinkage also get reduced. This is also another advantage. Of course, mixing has to be done properly because it's a very fine material which is in the colloidal form. So proper mixing is required. And if you are using silica fume, which is in the condensed form, and various studies says a normal mixer is not able to mix this condensed silica fume, because once it is condensed coming to the original sizes of submicron, it's very very difficult with normal mixer. That also we need to keep in that mind. Chloride saturation test is the only authorizing test which we saw. Even AS team is also saying, because nowadays people, if you see a few of the structure also we just shared with you, their recommendation is only RCPT. If RCPT is recommending is okay. If it is in conjunction with a 90 days long term testing, pond test, a correlation is being established, it is okay. If it is done purely for that concrete, purely RCPT values, which is not being recommended even as per ASTM also, that also we need to take into account, because combination of these both chloride saturation along with RCPT is being recommended. Durability and strength are greatly enhanced if fine and ultrafine material are used in concrete. This is how we concluded, and I think we understood from the earlier, you can say, slide and presentations. With this, I think I'm just concluding the presentation. Thank you all. If you have any queries, we'll just, you can say, see if we can see the chat box. Somewhere you can help me. Yes.
Okay, any participant want to ask any question, they can enter into in the chat box. So look like there is no question right now, but we will be sharing a feedback link with the participant.
Yeah, definitely.
Okay,
If any question come up
if
later on
any question
also,
comes,
definitely we would like
I
to
will
answer.
let you know through
Yeah,
an email.
yeah, yeah, definitely,
Okay,
definitely.
then we will conclude the session, sir. Then,
Yeah, thank you very much. Thanks.
thank you so much, sir, for your informative session.
Yeah, we'll leave. Yeah.